probably should, but...
Oh, that's...
I think so. I think they want you to keep...
All right, it's working.
It's great, but I wish they had at least commuters could exit early, because like I have a class right at 12, and I'd be more motivated to go to combo if I could leave like 15 minutes early, get up lunch, and go to class.
It worked.
Oh, it's an act. I thought it was a computer sound.
You might want to cover your ears. I muted it the first time. Was it? No, I'm not going to smack it really hard. What's that? No, I mean it's that's as quiet as I can make it. I'm still working on. Yeah, oh yeah, for a football game that'd be really obnoxious. All right, I will begin with a word of prayer now that I have your attention. So, Heavenly Father, we thank you for this day. I thank you for these students. Just pray you'd be with us, help us to glorify you what we do this day, and help us to just learn a little bit more about your creation together, Lord. In your name I pray, Lord Jesus, amen. So, Canvas does have like one redeeming feature, and that's that you can go to the assignment and like send an email to everybody who didn't do something or something. And so that's pretty much the only thing I'll use Canvas messaging for, because it's like automatic and easy. And so like I sent an email to everybody who didn't turn in mission 1 basically to say, hey, you can still turn it in for half credit. All right, I do offer you that. If you want full credit, you turn it in on time and such. But you can turn it in half credit. Now I would like to get all of the half credit assignments before the test. So like, because there's less point in doing missions 1, 2, and 3 after test 1, right? Missions 1, 2, and 3, completing them, working through them, understanding them is what you need to do, in part, to have a better chance at surviving test 1, right? Like if you don't sort through missions 1 through 3, then you're probably not going to have really internalized the concepts. And then I would say beyond that, it's, there was a few years ago, I don't know, maybe 10 years ago now, Dr. Skimbortis came to me and he told me about, he had these, I think it was like end of course evaluations, and there were some students in there complaining about other students. They said that they had an unfair advantage in the class. And I was like, really? Like how did these students get this unfair advantage? And well, the students who complained said that the other students, they had been working problems at the end of the chapter that weren't even assigned. And that gave them an unfair advantage. Now, I don't know if that was comedic on the part of the course evaluation. Let's hope for that. Let's hope it was a work of comedy. If so, bravo, we're still talking about it. But it is nevertheless true. Like, the more problems you work, the stronger you'll get at physics, right? On a personal note, for me, I took physics to start with at a community college, and I was kind of always able to do it, more or less, but I thought I could do it, right? And then, I got right answers, fine. But I basically got right answers from this sort of intuitive balancing of equations idea, all right? And then I started, I transferred to NC State, my third year undergraduate, after I'd done with my community college thing. And then I got a job as a physics tutor. It was that point where I sat down and was faced with the prospect of explaining myself to someone. That was the point when I realized I knew nothing. Because to explain someone, you have to actually explain how you're using Newton's laws to solve the problem, as opposed to just saying, well, these should match, they should balance out, right? So it's a process, right? And so I got better at it. Why? Because I worked more and more problems, But anyway, so, yep.
When's the exam date again?
When's the what?
The exam date?
The exam date, everything is on the course planner. So Did I give you a course planner? I can't remember if I did or not. Did I?
Yeah, I can't imagine.
I didn't give you one. I don't know if I have any still on me. They're posted, like, you know.
If we post on campus, I'll just print it out.
Posted on Canvas. Like, here's, like, page 1 of it is this, right? Just let you look at this for a minute.
You can have mine. I already have all the dates in my calendar. I just have like highlighted stuff.
Oh. So that has everything, and this also reminds me when I need to write a test. Oh, apparently like February 13th. Hey, that's the day before mission 1 is due in Calculus 2, isn't it? Huh. It's kind of all coming together there, isn't it? Sorry, I don't plan that. It just happens, you know. Maybe celebrate Valentine's Day like a week later or a week earlier, like, unless your, you know, significant other like really likes math and physics. I don't know if you're in both of these classes. Okay, listen, let's work a problem. Here we go. Oop. Oh, is the everyone's attended? Anybody not seen this sheet? There you go. All right, here's a problem. So this is example 1. And here I have mass M has position, all right, at time t of r of t equal to x naught e to the minus alpha t I hat plus parentheses y naught minus 1/2 gt squared j hat. All right? For some constants, x naught, alpha, y naught, all right? Then the question is, what net force causes this motion? What net force is responsible for this motion? Okay, so this is the counterpoint to the example I worked at the end of class last time, right? At the end of class last time, if I remember right, I gave you guys like the net force, right? And I said find the position. How did we do that? And what we do, we divided by the mass, we found the acceleration, then we integrated once to get velocity, integrated again to get position, right? This is the opposite way. Here I'm telling you, you know, here's the position, so let's find the, well, we can find the acceleration, right? And so the velocity is what? So we have to differentiate, yeah? Differentiate that, we get minus alpha x naught e to the minus alpha t I hat. And then minus gt j hat. Because the derivative of a constant 0, right? So that's my velocity. What's my acceleration? Differentiate again, right? So I get alpha squared x naught e to the minus alpha t I hat minus g j hat. So what's the net force that's causing this motion? What does Newton's second law say? F net equals what? Mass times acceleration. So we just take our mass and we multiply by that. And there you go. This is the force that caused the given position, the given path. All right, so there you go. So, okay, so just to make this problem slightly more interesting, can you tell me the dimensions of the constants involved? Tell me, what are the dimensions What's the dimension of alpha have to be? Let's say, or units, just to make it more concrete. We'll use kilogram meters seconds, okay? For alpha. I usually do like a square brackets for that just to denote the units. What would you say? Let me do an easier one. What's the units for x naught? If I'm using kilogram meters and seconds, what would that be? A meter, a second? What would it be? Meters. It would have to be meters because it's proportional, right? It's giving you the coefficient to one of the unit vectors. So if you have a vector, right? If you have a vector, the units of the vector have to match on all the components. Otherwise, you can't really add them together, right? You can't add apples and oranges. At least in physics, but maybe at a grocery store. But so this would be meters. And alpha, listen, so you have to feed exponential unitless numbers. So for this to be reasonable as a formula, alpha has to have units inverse to t. So alpha has to have units of 1/seconds. So this is what I'm doing right now is called dimensional analysis, all right? Okay, so great. Does this make sense then? What are the units of the acceleration? Meters per second squared, right? And that's manifestly so. Here this g is 9.8 meters per second squared as usual, okay? So that makes sense. It's got units of acceleration. How about the coefficient of the I hat? Well, you've got e to the minus alpha t, which is unitless, right? That's just a pure number. And then you've got alpha squared times x naught. What's the units on alpha squared x naught? Well, that's alpha squared is 1/second squared. X naught's got a meter. So this is also meters per second squared. So this is a reasonable expression. What I'm explaining to you right now is a way we can check ourselves. If we're doing something like a little bit sketchy and you have kind of a sense about what you're doing is wrong, one of the ways you could check yourself is just quick look at the units of the formula you're writing down. If you're doing something like adding meters to meters squared, well, you're probably wrong, right? The exception to this, of course, is those silly made-up math examples I've scattered here and there where I don't have multipliers, right? I have things like here the path is, the formula for the path is like t squared, t cubed, something like that, right? Well, dimensionally, that can't possibly be reasonable because t has units of second, t squared has units of second squared, t cubed has units of second cubed, so it's not really a reasonable formula unless we're working with like time where we're essentially thinking of, you know, we're suppressing the units in that system of notation, which we do all the time in math. Because if we always put multipliers in to make things dimensionally consistent, you guys would go nuts, right? If everything always had to have these kinds of, you know, alpha or some kind of multiplier here to make it unitless, then the formulas get messier. All right, enough about that. Next example I'll do for you guys. That was, by the way, example 1 from lecture 9, for what it's worth. Here's example 1 from lecture 10. And so this is kind of in between the Atwood machine and the hard problem I worked at the start of class last time. So here we've got a mass like so. All right, I'm calling that M2. And a rope goes up over this pulley, which is again frictionless because that's just the kind we got at the store this week. And then M2, like that, frictionless, massless pulley, an unstretchable rope again. The angle of inclination is theta. The question then is, find the acceleration of M2. And we're assuming frictionless because I've done enough of friction already this week. So I'm giving myself a break from friction today, at least for now. Maybe we'll get to air friction a little bit later. Okay, so that was supposed to be a straight rope. Sorry about that. Try that again. They clean this board with water or something? Goodness gracious, it's got all these streak marks. Okay, you guys can't see it. What? Which one? Oh, you can't see the contrast of M2 on M2? Yeah. Hashtag M2. So, sorry. I guess this was M. Well, What? Oh, duh. That was a 1. This was a 2. There we go. Okay, so let's find the acceleration of m1 up the plane. All right, how do we do it? So we're assuming no friction, okay? Rope, pulley, essentially massless. All right. Okay, so here we go. We have on M1, what's going on? Well, we've got on the one hand this piece, on the other hand this piece, right? So we've got oh my bad. Fine. So we have mg here, right? That's the total force of gravity, but it splits into 2 pieces, right? And I'll color code them here. So you've got the piece that goes parallel, right? Which is what? mg sine theta. And you've got the piece which goes perpendicular, which is like so. That's mg cosine theta. Yeah, you win some, you lose some. I'd like to have made this picture bigger, but I then again would like for some of you to sit closer so I don't have to make the picture bigger. So if you sit in the back, you know, you need to get some binoculars or something, whatever. Sorry about that. I can't shrink the room. I don't possess the technology. So, maybe if we had like a large inflatable bladder, we'd bring the edge and I just slowly inflate it, slowly pushing the students closer and closer to the board as the class goes on. All right, I digress. So that's how gravity breaks down the parallel and the perpendicular component. What else does that play? Let me just put it down here. It's easier to see. So M1, we've got this piece, mg sine theta down the plane, right? You've got the tension force going up the plane. You got the normal force like so, and then you've got your other piece of gravity, mg cosine theta like that. Right? That's all on M1. M2 is easier, right? On M2, what's going on? You got the tension force up, and you got M2G down, and that's all she wrote, right? It was more complicated last time because we also had friction, right? No friction this time, so this is it. These are the free body diagrams that we have to contend with. And of course, you understand that I could just as well just draw the single force of gravity like this, right? That was supposed to be, I tried. Try again. Golly. I need some like, that's still not right. Oh well, I give up. If I was doing this right, these two should add to give a vertical vector, right? The fact that they don't means that my picture's not quite right, you know? So like, probably this mg sine theta should be more like this, so that when I draw this tip to tail, so basically if I take this and shift it down here, like that, I should get a vertical vector downward, so the parallel part and the perpendicular part of the gravity should add together to just give you a downwards mg. But anyway, I'm splitting that red arrow into the 2 pieces because we don't really care. Well, anyway, let me stop this. And there we go. All right. So then, Newton's laws, right? What do we have? For M2, we have M2A equals to what? It equals to M2G minus T, right? There's Newton's second law for M2. And how about M1? You have M1 A perpendicular equals to what? 0, right? It's not flying off the plane. And then what's that equal to? What's at play perpendicularly speaking? You got your normal force, right? And you got your mg cosine theta. They're equal and opposite, apparently. So n minus mg cosine theta. So lo and behold, we find out that the normal force was equal to mg cosine theta, and that probably doesn't really matter to anything else. All right? Now, I am assuming, right, guys, I am assuming that this pulley is situated, right, so that it's pulling on the box parallel to the plane. That's important, right? If the pulley was situated so that it was pulling on the box at an angle to the plane, that would complicate things further, right? So I'm assuming that this pulley is situated so that you're pulling parallel to the plane, if that makes sense, okay? So what's the other Newton's law, component of Newton's law? The parallel part, right? So you have m1a equals to, in terms of the parallel, we have tension goes up, and that's the direction for positive A, in this case, as I've drawn it, and then minus mg sine theta. All right? And then what? I think the middle equation's kind of like, I don't care. Like we can pretty much, if we hadn't even written this down, it wouldn't matter, right? So this is kind of like, you know, whatever. It's not wrong, it's just not relevant to finding the acceleration to the problem, right? So to find the acceleration, what do we do? Look at these two equations, right? Add them. What happens when you add these two equations? The t cancels out, right? Do we care about the tension? Not particularly. So I get m1 plus m2 times a. The tensions cancel, and I get m2, you know, minus, and this was an m1. Was it m1? Yes, m1. These are supposed to be m1. Sorry, guys. There's a 1 in here. It's hard to see, but some of it's still in my marker. There we go. Fixed it. So gravity on m1 is m1g, right? Okay. So minus, my bad. I should have used a big M. All right, so when I add these, I get m2g minus m1g sine theta. All right, so here we go. The acceleration is m2 minus m1 sine theta, all divided by m1 plus m2, times g. And I'll get out of the way here, but there you go. That's the acceleration in this case. So this problem is a good problem to think about in terms of like limiting cases. Last class, the example 2 I worked, I think, was Atwood's machine, right? Think about this. In this problem, what happens when theta goes to 90 degrees? What does this problem become when theta goes to 90 degrees? It's the Atwood machine, right? What happens to a formula for acceleration when theta is 90? You get m2 minus m1 over m1 plus m2. That's exactly what we had for Atwood's machine, right? What happens, on the other hand, when we put theta to 0? What's that? If you think about it, if we put theta equals to 0, this becomes the tabletop problem, right? You got a pulley here. You've got mass 1 sitting on the table without friction. You got this thing going over here like so, right? That's theta equals to 0 for this problem. And if you work through that problem, I think this is in your homework, right? Maybe with or without friction, you should find out that in this situation, the acceleration is m2 divided by m1 plus m2 times g. So the sine theta term's just gone in that case. Of course, we could work that out as a separate problem if you'd like. Yeah? So I don't know. I think it's always an interesting thought experiment to try to think about special cases for a given thing, like extreme cases. Do they interlink? Do they make sense? And I think they do. All right, so let me get this thing out of the way here. Oh, by the way, I think I said it in the announcement, but to say it again, I am rescinding the you have to print on just one side of the page, because I said that announcement, some of you missed it, and you printed the missions for the whole semester, and then I feel bad because printing's not cheap, and well, I mean, it costs the same to print it single-sided and double-sided, though. They charge you 9 cents per printed page, not per physical page. So I think it's like 18 cents per double-sided page. It's not a good deal, really. Anyway, to get to the point, I'm okay if you turn in your homework on the double-sided, the printed. It does need to be on the printed assignment, though. Like if you just write solutions out on fuzzy paper, we're still going to take a bunch of points. I don't want to, but do please work out the missions on the printout if you would. And I think we're charging 10% for not stapling, so hopefully you'll start stapling it. It's, as we learned, what do we talk about? Second story, second floor printer lab, free staples down there. Woohoo! Have a free stapling party, I guess. I don't know. Let's see here. Where are we? Example 3? All right, so you guys, I feel like you deserve an example with some numbers in it. Here's one. Suppose you got a sled here at 30 degrees, and you got a little rocket car. All right. Here's a rocket car. And so it leaves here with initial velocity v naught, all right? And then let's suppose that maybe we can, just for the sake of discussion, make it a level plane here, all right? So I don't know, this is some kind of bunker that's built below the plane of the plane. And so the rocket car accelerates up this little ramp, all right, with a constant thrust. And so it's thrust, I say it's thrust, constant thrust, 10 times its weight. Okay, so that's the thrust on the rocket while it's on that. And I say the rocket fires how long? I say the rocket fires for 1 second. And the 30-degree ramp, all right. And then it turns off and it flies as a projectile. And then the question is, how far does it fly horizontally at the end of the ramp? So my question is, how far is this? All right, you're like, I thought you said there were numbers. Well, yeah, kind of. So what's there's a couple different things going on here, yeah? So we have the period at which the rocket's accelerating, right? It's accelerating up to the end of the ramp, and then it flies as a projectile past that point, right? So there's kind of a two-step problem. So to figure out the first part, maybe I should look at Newton's, I should look at a free body diagram for the rocket, So let me do that here. So basically you've got what? You got the force, the thrust force, which is going straight up the incline parallel direction, right? And what's acting against it? Gravity, but not all of gravity, right? Because you're really just going to have what? Mg what? Mg sine theta working against it, right? And I am not taking into account any kind of like friction, all right? So we can think of it as like a, we're just saying the friction is negligible, so we're not going to worry about the friction force here, all right? Yep.
Determine whether you use sine theta or cosine theta.
geometry. So the picture. So this is mg, right? This is theta. So if I break this into two pieces like so and like so, then this theta here is actually over here. And because of that, that makes this length here mg cosine theta, but this one up here mg sine theta. So it's just because of the way the angle reappears with respect to the gravity being downward. It's, yeah. So the perpendicular part is just going to balance out with the normal force. We don't really care since we're not worrying about friction, right? So that doesn't come into play for this problem. So the mass times acceleration during the the rocketing part, it's going to be the thrust force, right? Minus mg sine theta. Now, what did we say that the thrust was what? 10 times its weight, right? So that's what? What's the weight? It's mg, right? So we have 10 mg. And what's the sine of 30? It's a half, yeah? So this is minus mg over 2. So you got 9.5 mg. That's your thrust. So what's the acceleration? So the acceleration is actually 9.5 g. You go 9.5 g is during the process of it thrusting. And then we're assuming that the rocket starts at rest, okay? I haven't said that yet, but that unless something else is stated, you always tend to assume something starts at rest, right? If in doubt, you can ask me. I'll tell you. Yeah. Okay, so if it starts at rest, what's its final velocity? I mean, maybe I should say this v0 is really vf for the rocketing process, right? So v0 should be equal to, I'll call it v start, plus 9.5 g times t, yeah? But here, the t with t equal to what? At the start, it's a second that it's been firing, yeah? So, and I said the velocity at the start of the rocketing process is 0. So all we're looking at here is 9.5 times 9.8 meters per second squared times 1.00 seconds. What is that? That would be the initial velocity that the rocket leaves the ramp with and begin 93.1? I just believe you, but I went to the trouble of walking all the way over there to get this calculator, so I'm going to, as our last great president said, trust but verify. I'm not sure I really believe that. I'm not sure he was that great. Anyway, 93.1. 93.1 meters per second. Okay, so, yes, sir.
I guess we have to assume that it takes a second to reach the end of the ramp.
Yes, yeah, I said it's thrusting for a second and then the rocket fires for 1 second. And yeah, yes, it leaves the end of the ramp. In the words I wrote out, it says that. I just haven't written them all on the board here. I said, and it turns off and flies as a projectile. But yeah, you have to assume it leaves the end of the ramp. If I gave you more, you're right. If I had given you the length of the ramp, then we could work the more complicated problem of figuring out how much further up the ramp does it have to glide before it actually leaves and goes off as a projectile, right? And that would be a 3-step problem. I'd have to figure out the initial velocity that it's going as it's accelerating up the ramp, then the thruster stops, and then you're just stuck with a deceleration of g sine theta. Then that would chop some of that velocity down, and then it would get to the end of the ramp, and then it would fly as a projectile like that. That would be a more complicated problem. That's not the one I intend at the moment. Good question. So we are assuming, like you said, that it just gets to this is right here. T equals to 1 second, okay? From when the rocket fired. at that point. And then what happens? I've made our life easy in some sense because I said it comes back to where it starts at the same height, right? So what's the range formula? We worked this out the other day. Remember? Range is, what is it? It's 2 v naught squared sine 2 theta over g. Did I remember that right? I mean, we could derive it again, but let's not do that today. So there's I just work it out. And of course, I could be lazy and just go back to the symbolic one, but I'll put numbers in since that'll make you guys feel better about it. Let's see here. 9 times 93.1 meters per second squared. I got to figure out what the sine of 60 degrees is. Well, I mean, it's square root of 3 over 2, but whatever. Divided by 9.8 meters per second squared, what's that work out to?
16.45.
No. 93.1 squared times 2 times sine of 60 divided by 9.81 works out to 766.7 meters. Unless I have an error in the notes, which is possible. Now, wait a minute. There is no 2 there. You guys don't believe that? That 2 is already absorbed into the sine of 2 theta, right? So, yeah, there's no 2 there. The original formula was 2 v naught squared sine theta cosine theta divided by g. But then the trigonometry is that 2 sine cosine is sine 2 theta. That's where the 2 went in our original derivation. So this is the formula for the range, I believe. Now, with that adjustment, does that check?
Yeah.
Yeah.
Missed the squared.
Oh, you missed the squared, okay. But you did multiply by 2?
Yeah.
So you've still been wrong, but it would have been my fault, right? So it's all good. All right, so there's a problem. Shall we work another? Let's work another. I think it's time for a new character to enter the story. Let's see here. Get out there. Well, I didn't breathe it, but I did walk into the cloud. Okay, so springs. The spring force. We should talk about this because this is a pretty important example for physics, all right? And, oh, you got it. Thanks. So I should introduce you to what's known as Hooke's law. Hooke's law says that the force is equal to minus kx. This is the spring force law. Let me explain what that means. So here's the situation. You got a spring, all right? And it's attached to like some mass, okay? So let's suppose that is just the way it looks like in equilibrium, all right? Then, on the other hand, if you take that same situation and you stretch the spring out a little bit, right, that would look like this. On the other hand, you might take the spring and compress it like this, right? So, mass, mass, mass. And I'm assuming that this is like a a frictionless plane just for the sake of making it easy to think about, okay? And so here, in this situation, you know, we have x equals to 0. All right, and so what I try to draw these at the same way. So like the equilibrium position is this red line, right? And so if x is positive, so when you're in equilibrium, what's the force of the spring on the mass? 0, right? It doesn't do it, it just sits there, right? It's equilibrium. On the other hand, if x is positive, what does the spring force do? It wants to pull the mass back to equilibrium, right? So the spring force is like this, right? And so that makes sense, right? If x is positive, then F equals to minus kx is less than 0, right? And that makes sense because we're talking about one-dimensional motion, and a quantity less than 0 just means it points to the left, correct? So that makes sense. The restoring force points left. Now on the other hand, over here, right, the force of the spring points the other direction, right? And so down here, the x is less than 0, and if x is less than 0, then F equals to minus kx is in fact positive, right? That's how this works. So a compressed spring tries to uncompress itself and push back to the equilibrium. A stretched spring tries to pull back and, you know, again, get back to equilibrium. And then what happens if you actually, and this, supposing this is a frictionless surface, what happens if you pull it out and then let it go? What happens? It just does what? It oscillates right back and forth. This is called simple harmonic motion. All right? And we could try to solve Newton's law, yeah? We could try to do that. What would the equation of motion be if this is, if this is what's going on? If that's the only force on the mass, what does Newton's law say? It would be mass times d squared x dt squared equals to minus k times x. All right. You could rewrite this. What you're trying to solve is, x double dot equals to minus k over m x. And okay, so if you let omega equal to the square root of k over m, then it's easy enough to see that x of t equals to, a sine of omega t plus any angle you like solves it. Try it if you don't believe me. Solved. How do I know I solved it? Well, differentiate it twice. What happens? So if you're in my Calculus 2 class, in about a month or so, 3 weeks, somewhere in there, I will derive this through an integration procedure. All right? I shouldn't do that here right now. But I can tell you that this is the solution. And that's not hard because you can differentiate, right? If you differentiate this 2 times, what happens? Chain rule brings out an omega. The second derivative brings out another omega. So differentiating it 2 times gives you an omega squared. One of those derivatives is of a cosine that gives you a minus. So what happens here is when you take the second derivative of this, you get x double dot is equal to minus omega squared x. But what is omega squared? It's k over m, right? Which is to say that this solves the equation of motion. So that's why you guys just told me intuitively it goes back and forth, right? Well, there's the equation of it going back and forth. It's, sine of omega t plus phi. All right. Anyway, so there's just a little bit of the the calculus. And so admittedly, to understand, to master this mathematics, you have to take differential equations, right? That's where we do this in gory detail. Or maybe at the very end of my Calculus 2 this semester, we'll do that, all right? So, what happens when you hang the spring vertically? Listen, so solving the equations of motion in here, that's kind of tough for us right now because of where we are mathematically, right? But we can work all kinds of problems with springs. We just typically ask questions about equilibrium for now. After test 1, we'll learn about this thing called energy. And once we learn about energy, the secrets of the universe will be open to us. We'll be able to solve all kinds of problems we can't quite solve right now. And some of those will be spring problems. But until that time comes, we can talk about equilibrium for springs. That's fine. So, example 5, is it? Or 4, I can't remember. 4. So, simple enough question. You've got a spring, right? You hang a mass on it. How far does the spring stretch? That's the question. How far does the spring stretch? Spring constant K, let's say. I haven't explained where that formula came from, guys. I just pulled it from the thin air. This was by magic. This is math magic, right? The easiest way to solve a problem is to know the answer, right? It's called guessing. It only works for people who already know things. Not especially useful for people who are learning, but it nevertheless is true. That is the answer. Okay, so how about this? So we basically just have, what's going on here. We have the spring force, right, which is, let's say, Kx, and we got mg going down, right? If this is an equilibrium, how far does the spring constant, listen to me, spring stretch, constant, what's wrong with me? K is the spring constant, okay? So what I'm supposing I've drawn the picture in equilibrium, right? So, ostensibly, the x I'm talking about is if you disconnected the mass, right? If you imagine disconnecting the mass, the spring would not have stretched out as much, right? So I'm supposing that like this point, well, I need to draw 2 pictures to fully communicate the idea, but my point here is that the spring has stretched x distance. And if it's done that, that means the force it's putting on the mass is kx, pointed upward, okay? So if we have 0 is in equilibrium, right? Mass times acceleration 0, and that's what? Kx minus mg. So how far did it stretch? Pretty simple, right? mg over k, that's how far it stretched. So what this means is you can figure out the spring constant, right? For a given spring, how would you figure out the spring constant? You set it up somewhere, right? And what do? You could start with it and then attach the mass, a known mass to it, see how far it stretches. And then you'd have a decent estimation of k. That's probably not true. Probably what would be a better procedure experimentally is to hang I would start by hanging 1 kilogram on it, or 1 gram, whatever the appropriate kind of scale would be. See where that is, right? And then go to 2 kilograms and then see what the displacement was, right? Because if the spring doesn't have anything hanging on it at all, it's kind of all floppy and hard to gauge exactly where that is, right? If you hang just a little bit of mass on it, that kind of sets the scale, and then you can put some more, But anyway, that's out. Any questions? So. Let's see here. My final example for today is example 5. what if you have two masses? On a frictionless plane, and you put a force like this on M1. What's the force that M1 puts on M2? See, that would be what we call the contact force, right? And this is where Newton's third law, which we have not yet talked about before just now, comes into play. There's an equal and opposite reaction, which means that this contact force of M1 on M2 is matched by an equal but opposite contact force the other way. So if I draw on this M1, I have on the one hand the contact force of M1 on M2, and I also have the force F0 like that. Excuse me, I have the, my bad. Well, anyway. Oh, hey, say bye, Bell. So anyway, this is the next thing we need to talk about. Well, that's very generous of you. Thank you. Anyway, have a good weekend, you guys. Obviously, we need to talk about third law, so next time. Just wanted to get started.